Okay. How do we balance out the first one? What do we need to do? As it stands, the sodiums are balanced, but the iodines are not. So if I put a 2 in front of the sodium iodide on the product side, that takes care of the iodines, but now the sodiums are unbalanced. So put a 2 over here and I'm good to go. What about states? The sodium's solid because it's an element in its elemental state, and it says solid on the periodic table. The iodine, also solid. And the last one? How do you know that the last one's solid? It is. No, absolutely. 150,000% no. No.
It's on the other side of the It's on the other side of the equation.
Nope.
Salt.
It's a salt. It's an ionic compound. It's a metal and a non-metal. So you see metal, non-metal, you should just think salt and just immediately go, I mean, is there any water here? No. So then it's going to be a solid. Okay, so the next one, my oxygens are not balanced. So I'm going to need to manage the fact that there's an odd number on one side and an even number on the other. So if I double the potassium chlorate, then I can put a 3 in front of the O2, and that takes care of my oxygens. I've got 6 on each side. And then if I drop a 2 in front of the potassium chloride, then I'm good. So states.
First one is solid.
How come? You're correct. It is a solid. Why? It's an ionic compound. It's a salt. And the next one? It's another salt. It's another metal and a non-metal, so it's a solid. And then the last one, that's oxygen, so it's just gas. Okay. Next one. Looks like I can take care of my potassiums if I put a 3 in front of the KCl. But when I do that, then that gives me 3 chlorines. So I'm going to have to go back over to the reactant side and put a 3 in front of the hydrochloric acid, which was helpful because I needed 3 hydrogens anyway to be put in front of the phosphoric acid. And that's it. All right, states, what do we got? Come on, this is the third one in a row. It's a solid. Why? It's an ionic compound. It's metal, potassium, with an ionic polyatomic ion, phosphate, so that's a salt. So that's a solid. The next one? Aqueous. We had this discussion yesterday. The acid wants to be a gas, but would you ever just like spray gaseous hydrochloric acid onto this thing? Maybe, but most likely not. So you have used this in lab, and the way you used it was to have it dissolved into water. So the hydrochloric acid will be aqueous. So what do I have over here?
Solid.
Nope. It's not still aqueous, it is aqueous. Why is this potassium chloride aqueous when in the last problem it was a solid?
Because potassium.
Oh, because potassium is soluble, and I was hoping you'd start off with there's water there, and potassium is soluble. Absolutely, potassium is soluble all the time, but in problem number 2, there's no water anywhere. In problem number 3, we know there's water present because we put water in it when I put the aqueous hydrochloric acid in there. So when the reaction happens, that water is still present. And so now I've got the potassium chloride, and it would be a solid except it's wet, and both potassiums and chlorides are soluble in water, so this is aqueous. And the last one? What kind of substance is it? It's an acid. It's not a salt. It's H, not a non-metal, or not a metal. So it's aqueous for the same reason, right? Second rule on that list is acids are aqueous, or soluble, and so since water's present, this is soluble. Last one. Oh, we'll balance it first. 3. 4. 5. Does that look good? 3, 3, 8, 8, 4, 6, 10. Yep, okay. Okay, so first one, the C3H8. It's gas. It's, do we remember what I called that gas? Close. Propane. So remember why we knew this was a gas? It's covalent and it's small. Next one, it's oxygen, so it's a gas. Carbon dioxide, that one's obviously a gas. And it really doesn't matter if you put down liquid or gas for water, I'll just put down gas. Okay. Write the chemical equation for the combination of boron reacting with oxygen gas. So I have boron, that's a solid. It's reacting with oxygen gas, and it's going to make something over here that'll end up being a solid because it'll be a metal, non-metal, or it'll be an oxide. What else we got? How do we want to hook these things up? What's the formula of the thing that's going to be made? What charges do borons make when they go into a compound? Just +3, that's it. So the boron's charge is going to be a +3, so I'll write that over here. The boron's going to end up being a +3. The oxygen's going to be a what? -2. So I need to least common multiple the 3 and the 2, so it works out to be 6. So I'm going to need 2 borons because that would give me a +6 charge. And I'm going to need 3 oxygens because that'll give me a -6 charge, and then everything will be canceled out. So there's the formula of the boron with the oxygen. Somebody want to name it? Boron oxide. That's it. Nothing else. Boron oxide. Its charge is set at -3, so it doesn't change. So I don't need to tell you that its charge is +3. So it's just boron oxide. Okay, so we're going to use this equation, and I'm going to start with 75 grams of boron, and I want to know how many grams of oxygen do I need to use up all of that boron. So 75 grams boron. So for every 1 mole of boron, I need some number of grams of boron. .811. What does this first step do for us? Okay, why do we want to get rid of grams? Count number of B's. I just counted out the number of borons. Great. Okay, so I know how many borons I need because when this, we totally messed something up, didn't we? I forgot to do something. What was it? I didn't balance my chemical equation up top. I'm going to need a 3 here. I'm going to need a 2 here. I'm going to need a 4 here. So the reason I caught myself at that spot is because I need to know how many borons there are, because this chemical equation doesn't care about the mass of borons or oxygen. It needs to have 4 B's and 3 O2s. So the first step was for me to figure out exactly how many B's I have. So every time I have 4 borons, I'm going to need to put 3 O2s in there. And so I'm going to manage that by saying for every 4 moles of boron, I need 3 moles of O2. I want to make sure everybody writes down O2 and not just an O. So I know we're converting it into oxygen, but the oxygen comes in this form. So when you're writing down the substances behind these different units, it needs to be one of the substances that's up here in the balanced chemical equation. So if you just wrote an O, that's not up there. There isn't any O up there. There are only O2s and B2O3s. So what's this second step do for us? It gives me the number of O2 I need. The actual count of the number of oxygens I'm going to need for this reaction. But since that number is much too large for us to actually count, what is it, 30 seconds. $31.9988. And so then I've got the mass of the oxygen that I'm going to need. So that times 3 divided by 4 divided by 10.811 times 75. So this is 166.194 grams O2. Okay. So looks like I only have 2 significant figures, so this will actually turn out to be 106 or 170. So what happens when I put 175 grams of boron into a container with 75 grams of boron in a container with 170 grams of oxygen? They completely use each other up. Everything gets turned into the boron oxide, and I end up with 245 grams of boron oxide. No oxygen, no boron left in the container. Yeah.
So when you're writing chemical equations out, and maybe say use write an equation for boron, oxygen, just look at the charges first and then go from there.
Yep, that's it.
Okay.
Nothing else to it. Okay. So this is a combination reaction. I'll just write it down here. This B plus O2, and it's a B2O3. Combination reaction because 2 things became 1 thing. Great. I also said that it's a combustion reaction. Are we okay with that? Why is it a combustion reaction?
Oxidation is the same thing as combustion. Just the only difference is speed. This one doesn't have to be very hot to have. Well, it has oxygen.
Because O2 present is really your answer. So this is a combustion reaction. I mean, I guess I could have said that it's a rusting of boron. That would have been fine as well. So all this is oxygen reacting with the boron, taking electrons away from it. And so there's the reason it's a combustion reaction. Why is it a redox reaction? This guy's charge, this boron's charge was 0. It was just an element. This oxygen's charge was 0. It was just an element. And on this side, the boron's charge is +3, and the oxygen's charge is -2. So electrons were transferred. Are there 2 R's in that? Transferred. This one. So tell me about the electrons being transferred. Where did the electrons get transferred to, and where do they get transferred from? No.
Oxygen grabbed the boron's electrons, and that's why the oxygen oxidized the boron.
Correct. This oxygen has more electrons. How do I know that the oxygen has more electrons? It has a negative charge. The only way to get a negative charge is to have more electrons than protons. Over here, each oxygen had 8 protons and 8 electrons. Their charge cancels out. Over here, each oxygen has 10 electrons and still only has their 8 protons. So each oxygen gained 2 electrons. So these 2 borons, what happened to them? Each boron lost 3 electrons. So 6 electrons were given up by 2 borons. Those 6 electrons were accepted by 3 different oxygen atoms, each gaining 2 of them. And so the oxygen oxidized the boron. What happened to the oxygen itself? It was reduced. And I know that because its charge was 0 and its charge number went down to -2. We could go one step further. The oxygen was which agent?
The oxidizing.
The oxidizing agent, because it oxidized boron. What agent was boron? The reducing agent, because it gave electrons to oxygen. Okay, that's all I got.